And then, yeah, we can get started looking at this recitation six. So I'll just go in order and then Lily, we can like stop at four and five. And then if you want to ask specific questions about that, after I go through it, you can. But just looking at this quiz. So this is a bit, I was looking at it. It's a bit of a tougher quiz, I would say. Um, TA Wanchang prepared this recitation and added all new questions. So a lot of this is pretty new for us also. So we can look through it together. But here, question one, you should be able to get this from the PowerPoint, just looking at variables P and Q and obviously matching what they represent within the Hardy-Weinberg equations. Um, and then here's just a question two is a good practice problem for solving for q from q squared. So as you can imagine, you might, want to take the square root of that in order to find the answer. And then here's more of a application question for what you've already been looking at. So starting from this question, you obviously have 450 uh, bunnies with a straight-eared phenotype, but you can have two different genotypes. So that's kind of tough to start with. What you're going to want to do is start with the 120 homozygous recessive genotype, because you know that's Q squared. So once you start from Q squared, you'll be able to find both P and Q using the Hardy-Weinberg equations. Um, and then here you're looking at another application question, looking at a recessive genetic disorder. Um, and then here on question five, looking at, or actually, we can stay on question four too. Lily, if you had any specific questions um, on where to start with the random mating part.
Yeah, I'm a little confused on how to begin. I thought I did do the math right, and I asked an ATA, and they're also confused.
Yeah, so this one, like I will say, four and five are the ones that looking over the quiz was a little tougher. Um, but looking at genotype little a causes the disease at 2%. That's what that says. Yeah, so little a. I think this is the only place where you can start is that's going to be Q squared, right? So if you say Q squared is equal to 2% or 0.02, let me see here actually. Yeah, so if you start with Q squared being 0.02, I think
Why won't it be Q?
just because the genotype little a makes it Q squared. So then if you
Oh, okay, genotype versus allele. Okay, got it.
yes, yes, definitely. Um, so once you have that affected by the disease, I'm trying to figure out what step to get right after that. What were you thinking when you were starting this question?
I did the same thing, except I put Q, but I meant like Q squared. 0.02. 1 minus that equals the P squared, and then I would put it in the formula. But
Okay,
then I didn't know how to figure out the 2PQ.
I see. So you know what, I'm gonna pull out a calculator and because I haven't worked through these yet either. I'm actually curious how because if you do one minus that, um, well, you can find Q, right? So that's gonna be the square root of 0.02. But carrier frequency. Yeah, so if you find that, you should be able to find P also. Wait, actually, no, you might have been right. So the part that's messing me up too, I guess, is that it says the carrier frequency for a recessive genetic disorder where genotype little a causes the disease. Oh, so that's just saying that little a causes the disease. Man, I'm confused about this too, actually, now. Meg, do you have any ideas on how you would start this question? I don't know if you had any input, but I'm actually a little lost on this one.
Yeah, Christopher and I try to work at it, but if there's information missing.
Okay, gotcha. Yeah, because one thing that I'm struggling with is if you're a carrier, that means you're heterozygous, right?
Yep. Yeah.
So I guess 2PQ equals, yeah, you would have to assume things as you go. So, um, so you would have to assume that the frequency of, man, I don't know actually. Possible there's no AA right now. Like, are you saying there's no homozygous recessive individuals? Right.
Hey, can you hear me?
Yes, I can.
Oh, okay. Hey. Yeah, so I looked at this one too, and I don't think there's any way to do it unless you've got one other piece of information, either the frequency of the homozygous dominant or homozygous recessive. So I'm wondering if he made an error in giving the frequency of the heterozygotes instead of the homozygous or something. I'm not exactly sure, but honestly, I've looked at this one for a while, and I think you there's definitely something missing in order to solve this one.
I would agree. So this is due at midnight. I'm, does anyone know off the top of their head if Wansheng, the TA Wansheng has office hours today?
I don't know. I should have emailed him already, but I don't. I've never contacted him before, so I not having a prior relationship with him, I just didn't feel
Right.
comfortable reaching out exactly. So
Yeah, just out of the blue, especially yeah, about something like this.
yeah,
I'm gonna pull up the announcement from Dr. Holacek real quick. But I think you're right because I started with assuming Q squared was zero point zero 0.02, and I think that's the
exa
only way.
exactly. That would be kind of like the only way maybe we could do it. But he said the carriers had that percentage, so.
Right. Okay, so no, TA Dominic actually has office hours later today. Not one. Yeah, Wansheng doesn't have office hours until Wednesday. Okay, so let's see if we could figure this out. Where what he was thinking.
The only other thing I could think of is that maybe he's saying that there's no one affected right now, so that your homozygous recessive, your afflicted population would be at 0% right now.
But that is a
Um,
huge assumption, especially with
right?
students who are just learning this.
Oh yeah, yeah, for sure.
Oh yeah, yeah, definitely.
No, 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 we're with you. Sometimes these errors happen and some typos happen, so it's not a big deal. You guys will get it'll get corrected somehow. So
Yeah, we have our TA meeting tomorrow, and I'll make sure to bring this up, but we can always drop this question also.
Okay.
Yeah, I think that's what might happen. So, but we'll make sure that we go through this because um this is a bit confusing on where you would start from this. Because if you start with 2PQ, because that would be the carrier being zero point zero 0.02.
Mhm. There's no way you can separate out from there to find anything else. I mean, at least not that I'm coming up with. Again,
Yeah.
maybe Wang. I'm not sure how to say his name.
Yeah, I think it's like
Um,
Wansheng. Wansheng.
Wang Chang. Yeah, I'm not
Uh-huh.
sure if he has a different method for this, but this is something that I'm familiar with being able to solve, given just that. Anyway, all right, I'm going to mute myself again.
Thank you, Christopher. I appreciate that.
Yeah, no problem.
Man, this is, I'm just going to stare at this for a little longer and see if I would even know where else to start. But yeah, definitely at
Okay.
this point, affected by the disease. So being affected by the disease, you would have to be homozygous recessive. Okay. Man, yeah, I'm actually kind of stuck here too. Because you're right. If you are given that 2PQ equals 0.02, I don't know of any way you could solve for P or Q separately because you would have to assume that there's no one with the disease itself, but they're still carriers. So there's obviously still something for Q. But okay. Yeah, I apologize for not having an answer on that.
Yeah,
That's
and then
okay.
I guess my only other comment is that I mean it doesn't even really say if you're under Hardy-Weinberg or not. It does say under random mating, but that's only one condition. So I'd rather see the question read clearly whether or not you're at Hardy-Weinberg as well.
Right.
So that's another confusing aspect to the problem. But yeah. Okay, that's my last comment. Again, I'm going to go ahead and mute myself. Sorry, because I'm doing other stuff and I don't want you guys to hear everything in my background. So.
Right, right. So since you guys showed up to office hours, like obviously you guys are pretty dedicated to wanting to solve this question. One thing that he does provide to other TAs, I don't know how he gets to this step, but I'm going to give you this part of the question because I don't know where else you would go. Somehow you find out that the allele frequencies Q is 0.01 and P is 0.99. If you guys want to write that down, because then that'll give you the disease, you'll be able to find the disease rate from that, um, which is going to be Q squared. Let me know if I need to repeat that.
Oh yeah, for
The
sure. With that
Q,
information, you're going to be able to solve it.
Right.
That's not a problem. So where did you get that off the Dropbox or something?
That was off of, yeah, it should be on the Dropbox. I'm actually
Oh,
on
okay.
this right now because I think since I don't know, so as like like a observer on Canvas, right? You're an observer, right?
Yeah, I'm an ATA.
Okay, yeah,
Right.
but on Canvas it has you guys as like observers. I don't know if you can like edit
Yeah, I can't
quizzes.
see that part. I do have the Dropbox, but I think that only gives the answer, so I don't know if I can see his work or whatever throughout the problem.
Gotcha. So I'm gonna look at the Dropbox to see what it has because usually I just like since we can edit the grad TAs can edit the quizzes themselves, we're able to see like comments that he has
Okay, gotcha.
like
Yeah,
for
because when the student reached out to me, I was like, wait, is there any other information? Was there something from a previous question that I'm missing? Or, you know, is this a continuation of a different question that has other information? I don't know.
right. Yeah, so ooh, one sec actually. Yeah, so I don't think he updated the Dropbox like with his questions. Actually,
Okay.
okay, so if you go on Dropbox, it's actually question number one on this worksheet.
Okay.
Where for recitation six questions, the PDF that he uploaded. So if
Okay.
someone asks it like again today, you can probably refer to that, but it only has three of the questions. Um,
Okay. So if someone reaches out to me, I'm free to go ahead and give them that extra information. We've got what did you say it was again? I'll just write it down really quick. Q is
so Q is zero point zero 0.01 and P is 0.99. And I'm really trying to figure out how the only way I could think of is if you have 2PQ equals zero
well,
point 0,
are
like,
you sure that's not P squared and Q squared?
yes, I'm sure.
Oh, okay.
can you
Huh.
still walk through the formula? Because I'm still a little confused. Because the formula is still giving me a little trouble.
Definitely. So are you talking about the formula, like the Hardy-Weinberg formula, that's p squared plus 2pq plus q squared
Yeah.
equals 1? So ultimately here, let me see if I could pull up. I'm going to stop sharing this real quick and then pull up the slides. Let's see. Thanks for hanging in there, guys. Because yeah, that was a interesting question. So this is all with the allele frequencies. So ultimately, if we're looking at P and Q, I believe other formulas are that, if you find P, you're able to find Q because you can do like 1 minus
Yeah,
P.
one minus. Yeah.
Yeah. So when we're looking at two individuals mating, you have to look at all of like two heterozygotes mating. You have to use this formula, and it's almost like it's kind of weird because you are using genetics and math at the same time, like calculus. Um, and when you have allele frequencies from two individuals, you like kind of like multiply them together, and ultimately that's how you're going to get this formula. That's at least my understanding of it.
Yeah, I think I'm just confused on the question where you say Q, we're giving Q and P in 2PQ, but I don't know what to put for P squared and Q squared.
Which one is that one again?
Still question 4.
Oh,
Yeah.
still question 4.
Yeah.
Right. So you are given P or 2PQ. That's the only thing that it appears that this question is giving you, unless there's some wording in there that we're supposed to assume something else. So the problem with this question is that there's no way to get to P squared or Q squared from 2PQ, at least to my knowledge.
Okay. Well,
Yeah.
even with the information you gave us with the Q and the P.
Right, right. So if you have 2PQ equals zero point zero 0.02, all right, you can divide by 2 and you get PQ equals zero point zero 0.01. But at this point, we don't know, like we need
Um,
either P or Q to solve for either one.
Okay.
So that's why I'm thinking there was a typo on accident because ultimately you do find you're supposed to find that Q is zero point zero 0.01. Um, which then from there you just find Q squared and that's the answer. But yeah, that's the problem that Christopher is talking about too, is that you have to assume that P or Q is
something.
something else.
Yeah.
Yeah, maybe you can assume. No,
Mm-mm.
because you would have to assume that there is no Q, or like P would have to be 1. Like if it's a genetic disease, maybe everyone's who has the genetic disease has passed.
Has passed away because it's congenital or something, and
Yeah,
so yeah, I don't know. Um,
yeah, I don't like that either.
but even if you assume Q was zero, then you can't square zero. I mean,
You can't. No,
or I mean, yeah. Uh, well, Q wouldn't be zero because you do have a 2PQ of 0.02.
right.
But if Q squared, if you assume Q squared was zero, I'm saying you can't take the square root of zero. Um, and then let's see. So then if you're given Q equals 0.01, we could square that to get Q squared of 0.0001, and we can square 0.99 to get P squared equals 0.9801. If we use that, we would see that 0.9801 plus 0.02 plus 0.0001 does roughly equal 1. So that kind of satisfies the Hardy-Weinberg equilibrium equation there.
Right.
So I could see those numbers working out in the end, but again, I just don't. He didn't give them, so there's no way the students could have gotten that.
Yeah, I agree. Yeah,
Okay.
sorry about that question, guys. Probably should have
All right, Luke, I'm going to cut out. That was the whole reason I joined this session was to try to get some more insight into that question.
gotcha. Yeah, did anyone ask you about question 5 as well? That was the
Uh, oh, shoot, I have to remember now. I think it was either 5 or 6. Is that the one with the ratio?
Yes.
Yeah, this is the
Yes.
one I also asked you about.
Oh, you asked me about it. Okay, that was you.
Yeah.
Okay, yeah. So the ratio one, that took me a long time, but I was able to come up with a way to solve that. It's I wouldn't expect you guys to be able to go through all those steps that I did, but there is a way to solve it. It kind of involves because he does give you the four options. So you realize that the current ratio being 6 to 3 to 1, I think it was. Um, there's only certain possibilities with those answers that he gave you that would actually work in the end. So if you kind of test the different probabilities, even like you test the extreme cases of it, you would see that because basically your homozygous dominant, your AA, right? That's going to have to increase its ratio in the next generation, given that there's such little right now in the homozygous recessive and they're not allowed to mate. So there's really only one combination of those numbers that makes sense in the end. Again, it's pretty difficult to get there though, especially if you're being new to all this. So I would probably reach out to Wangxing on that one too, maybe just on its level of difficulty. But again, I mean, it is possible.
Okay.
So I guess my last hint on that one would be your current ratio, right, of your homozygous dominant to your heterozygous is 6 to 3, which is a 2 to 1 ratio. You're not going to have that in your ending result. Let's put it that way. That won't be possible given the current ratios and the fact that you're keeping the homozygous population out of the mating because you're not giving it an opportunity to combine and make new heterozygotes. The only way you can make new heterozygotes, let's say, is if the heterozygotes mate with other heterozygotes, and in that case, it's only 1/4 of those. So if you play out a couple of different scenarios and you say, okay, so like I chose a population of 100 because it was pretty easy to work with. Let's say 30 of the homozygous dominants mate with the other 30 homozygous dominants. That's an extreme case. You'd only get homozygous dominants from that. There's no other possibility. And then that would leave the remaining 30 heterozygotes to mate with themselves. That would give you a certain population. And then you can play around with the numbers and then look at the other extreme. What if all the homozygous dominants mated, or at least 30 of them, let's say, mated with the 30 heterozygotes? You would get those percentages. That would leave you with 30 homozygous dominants, 15 mating with another 15. Okay, so that's how I finally got to the answer on that one. Does that make sense? That's a lot to do, I know.
Uh, not really, but I'm more of a
Okay,
visual person.
I gotcha. Okay.
Yeah, I have a question.
Mhm.
This is my first time taking this class, and yeah, I was like, are you guys allowed to like write this out? Like, I feel like it'll be like I'm listening to what you're saying, but I'm just getting lost.
Definitely.
Okay.
I know there's like a whiteboard option. Christopher, would you be comfortable doing a whiteboard? I don't know if you've ever done it before.
I don't know if I have that option right. Right now, I'm on my phone. I'm mobile right now, so I
Oh,
don't even have
gotcha.
a laptop. Um, however, let's see, what could I do? I tell you what, if you guys reach out to me later on Discord, I can. I think I can text, some of my work to you and how I got there. That would probably be my only option at this point.
I see. Yeah, because I know some people use whiteboard options. That's if they have like an iPad though. Like I know TA Dominic does a lot of illustrations. So because this is like also my first time actually TAing this course as well, I am realizing like annotating is gonna be or like being able to
Yeah.
type out is actually a lot better. Um, so I think I'll be investing in like an iPad or something because it would be so much easier just to have like a pen, like an Apple pen and just writing around.
Yep.
Let's see though. So, Christopher, you said you were starting with
So
um
I gave it a population number of 100, right?
okay.
Let's assume a population number of 100.
Hmm.
Out of those, 10 are going to be the homozygous recessive that don't mate.
Okay. So we have 10. Oh geez. Let's see how bad this is. I'm trying to use like my cursor.
Mm-hmm.
So you're saying these are like the 10 little A's? Okay.
And I think you'll have then 30 heterozygous. We'll give that a big A, little a.
Okay.
And then we had 60 capital A, capital A.
Perfect. So then from here, so this is like the like parental population, right?
Correct.
Okay.
Okay, so then there's a couple of things we can do here. We know that the 10AA are not going to mate, it says.
Yeah, so
Am I
they're
okay?
done.
Yeah, go ahead and cross them out.
Sorry, guys. Yeah.
All right, so let's look at a couple of different scenarios, right, of how we could get these numbers. And what I like to do is I like to take the two extremes, one at the top and kind of one at the bottom. So in other words, let's assume that of these 60 AA right now, 30 of them mate with the other 30 AA. Does that make sense?
So
That
30
would give a new population there that only resulted in AA. Does
like
that make sense?
the big A's?
Yeah.
Okay.
Sorry. Yeah.
So
So
if,
why is the AA the dominant one, why is that 60 and not the A little
I
a
think it
60?
says 0.6 is the frequency, right? So if you have
Oh,
a
oh,
so
I
if you
see
have
what
a
you're saying.
0.6 frequency out of 100, that would give you 60.
It's with
yeah, isn't it the
Yeah.
other way around?
It,
the big
Oh, is it
A,
the other way
little A.
around?
I see what you're saying. Yeah.
Okay, yeah, I'm sorry because I didn't read over I'm just going off of memory right now, guys. Sorry.
No, it's okay. Thank you,
Thank
Christopher.
you for correcting me,
Yes.
whoever saw that.
Okay, so we have 60 heterozygotes, 30 homozygotes. Okay.
Okay, so let's assume then out of let's look at the dominant one first. Let's say 15 of those, they all chose the other dominant AAs, 15.
Okay, so 15 of the homozygous dominant.
This would be how we would get our least possible amount of heterozygotes in the next generation. Does that make sense? This is how I'm approaching the problem.
Okay.
Because you would have all of those mate with each other. So say 15 of those mate with the other 15, that would leave then that the 30 of the heterozygotes mate with 30 of the other heterozygotes.
Okay. Okay, I see. So they're gonna
Do you see where I'm going with
cross
this?
with other ones. And then so all the heterozygotes are gonna mate as well.
Mm-hmm.
Okay. Man, this is where like a touchscreen would be so nice. And you said you're assuming you said you're assuming this because
I'm just playing out different possible scenarios,
yeah.
and this will give us kind of limits to look at, and then because the answers are limited to certain choices, then you can narrow it down.
Okay.
So in this case, right, all of those 15 AA times the 15 AA are just going to give you more AAs,
Right.
right? Okay, out of the 30 AA mating with the other 30 heterozygotes. Let me say it that way so that we're clear.
Okay.
So 30 heterozygotes now mate with another 30 heterozygotes.
Yeah.
1/4 of those are going to result in the homozygous recessive. One fourth, yeah, and then 1/4 will be homozygous dominant, and then
Yes.
we'll have 1/2 heterozygous again,
Right.
right?
So this is like population one or
Yeah, F1.
generation one. Yeah.
Yeah, yeah. And that's what the question wants, right? Is what are the new ratios in F1?
Okay.
So now you can see that extreme play out. All right.
So yeah, these
So
one.
that gives you a certain ratio possibility.
Okay.
All right, keep those AAs in there. You're going to
Oh,
need those. Don't cross those out. Those are in the next generation.
sorry. It is. Okay.
So
Okay.
I have a
And
question.
yeah.
Hmm.
So okay, the reason why you're saying like the 1/4 recessive AAs, like you're basically just breaking it down, like if I do the Punnett squares, will I get the
Yeah,
same answer?
exactly.
Okay.
Yeah.
Just back to Mendelian ratios here.
Okay.
Okay. So now if we look at it the other way and we look at how would we end up with the max number of heterozygotes, we would
Mhm.
want to, we could mix in, we can say some of the homozygous dominants mated with the heterozygotes. So let's say 30 of the homozygous dominants mate with the 30 heterozygotes.
Okay. So 30 homozygous dominants
Mm-hmm.
times the 30 heterozygotes. Okay.
So this is another possibility of what could happen. And
Yeah.
I'm just, again, I'm playing out both the extremes because once we know the extremes, we know what's possible. And then anything, in the middle could have happened. Now, what would that leave you with? So that leaves you with 30 heterozygotes left from that initial population that have to mate. So let's say 15 of those mate with each other. So 15 heterozygotes times 15
Okay.
heterozygotes.
Gotcha. So we're still looking at the original population at this point.
Right now, yeah. But now we've accounted for all of the ones who can mate. Because
Gotcha.
again, we crossed out the 10 homozygous recessives. So it says they're not going to mate again. And that's kind of the big clue to this.
Okay.
Once they're out of the mating question, there's only a certain set of those numbers that's going to work in the end, the ratio.
Right.
So again, you would use those Mendelian ratios and you would look at these two, and you're going to notice that your ratio of homozygous dominant compared to the heterozygous has to change in favor of homozygous dominant. So since you currently have a ratio of 6-3, which is 2-1, in favor of the heterozygotes over the homozygous, you know that that's not going to be the case in the next generation, if that makes sense.
Could you actually
So I think the answer choices for each box are, let me make sure of this too, because I got this information from the student.
Gotcha.
Are the answer choices for each box limited to 4, 3, 2, and 1 or something like that?
Yes, they are.
Okay. So obviously, out of all those numbers, we know that 1 is going to have to be the homozygous recessive.
Yeah,
It's going
because
to have to be the less.
ultimately, yeah,
Yeah.
ultimately, yeah, okay, I see what you're saying.
Okay, so now we just need to figure out what is the proper ratio with the other two. Right. And
Gotcha.
so since the original one was 6-3, we know that the final one has to be turned in favor of homozygous dominance, or the dominant allele, the capital A.
Hmm.
Does that make sense? So there's only one really possible answer after that.
Okay. Oh, the 6-3 ratio, you're looking at the
Is
original.
the original, right? So that's a
Okay.
2-1 in favor of the heterozygotes in the original, but the F1 is going to be skewed towards you're going to have more homozygous dominance in that new population, given these possibilities.
I see.
There's no other way around it.
Okay.
Because when capital A mates with capital A small a, you've got a 50-50 chance of either capital A, or the heterozygotes. And
Gotcha.
when the heterozygotes, if they all decided to mate with each other, again, you've just got a certain number that you can come out with. So either way, it's going to be skewed back towards the homozygotes. So you will not have a 2-1 ratio. You're going to have something different, something where the homozygous dominants are represented with a higher number, a higher ratio. So if you give the homozygous recessives the 1, then those other numbers are only going to be able to combine there in the end one way. But I don't want to give away my final answer.
Okay. Do
That's
you
how I got.
okay.
That's how I approached the problem in the end, and felt comfortable with an answer that I would have given if I was given this test question.
Okay. I see. Do you were you looking at the answer key when you were going through
No,
this
no, I
question?
didn't even have the answer key yet.
Okay.
So let me go ahead and look at the answer key, I guess, if I
Right,
can get
because
to it.
yeah, I totally see your train of thought as well.
Is it
But
not matching up with the answer?
there's something like I don't know if it's exactly matching up with what I was thinking was going to lead to this answer.
Oh, okay.
So, Lauren, I'm just going to let you know it's not two, but by the end of this, we're going to make sure you guys have that answer. Okay, so the way Wancheng wrote this question out is that you are eventually supposed to go back to the Hardy-Weinberg equilibrium. Let's see what tools I have with this annotating. Thanks for hanging in there, guys. Also, the annotations are new to me. I wonder if I can. Oh, that's what I was wondering if I could do. Oh my gosh. Oh,
It
I don't know what that looks like on your guys' end. It was probably crazy.
looks like Transformers language.
Wait, it totally did, huh? Okay, I'm gonna move this over here to the side, just so we don't lose it. Oh, sweet. Okay. So also, Christopher, I don't know if you saw the answers. Were those the answers that you ended up getting?
No, I'm still having to go find them.
Yeah. Yeah, I imagine it's kind of hard on the phone. So
Yeah.
the way you can start with this question is that obviously your heterozygous individuals, heterozygous recessive individuals, little a, they're not going to reproduce. So you don't have to factor in this percent of the population. So what you're going to be left with is the zero point 0.3 here from the homozygous individuals, homozygous dominant, I mean, and you're going to be left with the heterozygous individuals, ultimately giving you 0.9. So you're going to be working with 90% of the original population.
I agree with that.
So within this 90% of the population, we're going to find the allele frequencies. So big A, little a. So let me see here. We're going to, so another thing that we can actually
Well,
calculate.
again, though, but he doesn't even specify that it is at Hardy-Weinberg equilibrium. So is that just, are we assuming that now
I
to be
guess
able to finish this?
there should have been a sentence saying that this population follows
Gotcha.
equations.
Okay. Now, if I would have had that, I might have approached it a little differently.
Yes, 100%. So if we do reuse these questions again, like on an exam or something, we're going to make sure that it doesn't look like this.
So for the
Hmm.
sorry,
No, you're good.
Hardy Weinberg,
Hmm.
what like words are we looking for to make sure we're doing that exact formula? Is it like the fruit fly population frequencies? Is that the key?
No, normally it's given to you. It'll say outright, assume this population is under Hardy-Weinberg or don't assume.
Yeah.
The only other way is that if it also gives you those factors, that make it under Hardy-Weinberg, like what are your factors? Very large population. You have to assume um, random mating. If all five of those factors are also given to you, that's another way of telling you it's at Hardy-Weinberg or not. But a question like this that doesn't have any, yeah, I that would not be kosher.
Right. So,
So, mhm.
sorry, what?
So just
Sometimes this happens on these recitations. When I took the class, there were a couple of problems that they had to look back over and correct, and then it got fixed. So,
yeah, I feel like I just get, like I said, it's my first time taking this class, and I just get really thrown off when it's just the problem. It doesn't really have like a
I hear
formula
you.
or just like I just get
Yep.
really thrown off.
Yeah. No. Yep.
For sure. Yeah, me and Wang Sheng, it's our first time TAing this course. And so we're kind of learning what, you know, this genetics course should look like, especially for people learning it online because you're not, actively in like a lecture seeing things written out for the first time. So
Yes,
it's
I think
also a bit
it's
different.
mine is hard. Yeah.
Yeah. Yeah. And this is a really hard course too. So, um, and like fast paced also. So even if it wasn't fast paced, this is hard material to learn. So it's okay if you feel like a little stuck on these questions because I mean, I'm a grad TA and I'm looking at these questions. I'm like, I don't really know about this one. Yeah. So we do try to give you like the best tools possible to succeed. Um, there should have been hints here, like hint, this is a Hardy-Weinberg. It should outright tell you if it's Hardy-Weinberg,
Yeah.
or it's going to be pretty obvious that there's random mating. There's no other factors that
Right. Because if it's at Hardy-Weinberg equilibrium, and then that's going to mean that the allele frequencies will not change in the next generation, and this becomes a pretty easy problem.
yeah.
Well, for me, I'm sorry, not for you guys, but I've done this stuff before. I'm still downloading the Dropbox, Luke. It's taking forever.
No, that's okay. Right now I'm trying to figure out how, okay, so ultimately, this is what we can start with in my eyes. Let me know if you guys think of anything else. So at this point, we can assume these that out of that 90% that we're actually interested in, because we kick out the 10% of homozygous recessive individuals, 1/3 of them are going to be of like the original population of this point 0.9 are going to be homozygous dominant, and then the other 2/3 are going to be heterozygous.
Yeah.
Let me think here. So this is p squared. And this is 2pq technically, if we use Hardy-Weinberg equations. Now there's one step here between this and where, the answer is actually workable because we're going to try to find the frequencies of like big A and little a. Once we find that, we're going to be able to figure out the proportions of big A, big A, and little a using Hardy-Weinberg equations. But right now, so at this point, with the equations that you guys learned, have you only been told that P equals like 1 minus Q? Is there any other way to solve for P or this big A?
From what I can remember, yeah, but also this is a section I'll have to go over. But pretty much all we told were E plus Q equal 1.
Yeah, because
Yeah,
that's
that's
all
the
I
only one.
remember. Sorry, what was that?
Yeah, same. I was gonna say that's the only one I.
So that's the only one I remember. Also, and there's some other equation that is used to solve for this question.
If you look at his notes for recitation 6,
Mhm.
there is a page that gives all the equations.
Oh, like the page before this.
Yeah, it should all be on there. Let me look that real quick.
Gotcha.
And then if it's not on there, then they wouldn't have been given it.
So I'm going to look at that as well to see if I should just give what he wrote down like right away, or if there's a way to kind of connect this to what was
Yeah.
taught in like the video.
Because his next office hours aren't until Wednesday, and this is due tonight. Is that right?
Mhm.
Okay. Okay, let me open up your guys' course again. Okay, I'm finally back with my laptop, so I might be able to work a little quicker now.
Thank you.
All right.
Using that genotype counts. So there is one equation that is on the actual page where he has his video. If you scroll all the way down to the bottom, you can see that the allele frequencies using the genotype counts, we don't have like genotype counts specifically, but there's ratios which you can kind of use in place of counts. And we're interested in this numerator. The numerator here, I'm just going to write it down real quick. Let me memorize that. I think this is how he got to this point in the question. So the numerator is that P equals 2 times like AA. So that's going to be like 1/3 for us.
Okay, you're looking at that bottom left box.
Yeah, and it's plus the heterozygous genotype, right?
Right. And of course you're only using one. There, you're not timesing it by 2 because you're just using half, because only half of those correspond to the capital A, if that
I see.
makes sense.
Okay.
Right. And now we're dividing by the total number. That's why when I did this problem, I translated it into a certain number for the population. And I thought that either 10, a total like n equals 10 or n equals 100 would be the easiest to work with.
Right. Now that I'm looking at this, I don't know if it actually comes out to what I thought it was going to be. So, okay, so you were using like an actual number.
Yeah. Yeah, I gave it a number. So in other words, if we use this equation down here for p, we're going to have 2 times, let's
It'd be
see.
2 times
No,
1/3.
you'd have to use the frequency there. So 0.3, 2 times 0.33, 2 times 0.33 plus
Yeah.
your, what is it? 0.66.
Yeah. So at that point, it's going to give
Okay.
us more than
And
one,
then you're
which
good.
is where I'm getting confused.
Mhm. I think I might have tried it that way too, and I backed out of it because of that. Yeah, the only way that I came up in the end was the way I tried to describe it to you guys, but that's super complicated. I'd be interested in talking with Wang Sheng about this problem as well.
Yeah, me too. So the way Dr. Holacek kind of divides up who makes what recitation is just kind of like on our background. So Wansheng is like a genius when it comes to population genetics. That's kind of what,
Right. So I'm sure he's like got some other stuff to be
yeah,
able to do this. That's what
right.
I was figuring too. So
So
I'd
ultimately
say we
though,
just table these two until we can get back with him.
yeah. Yeah, so I mean, at this point, I'm just gonna write down a couple helpful pieces of information that'll get you guys to like the right answer. You're still gonna be practicing Hardy-Weinberg equilibrium, but what you'll ultimately find, also, I'm gonna get rid of this because that was not helpful. Okay. No. Oh, there we go. Okay. So we eventually are going to be able to find somehow that the proportion of A, which is going to be the same thing as P, right? That is going to equal, let me double check. Okay. That's going to equal 2/3. And then you're going to find that the proportion of little a, which is Q, is going to be 1/3. So this is where I'm a little stuck in how you go from this information that you have on the top that we were talking about with homozygous dominant kind of representing 1/3 of the mating population, and then your heterozygous population representing the rest of the 2/3. From this, you're able to get to find that P equals 2/3 and Q equals 1/3. That kind of looks like A equals A. It's like I'm going to redraw that Q. And from there, you'll be able to find that um, you'll be able to find AA or AA, big A, or P squared. That'll give you a ratio. Little a will give you a ratio. And then you'll also be able to do, let me double check this, 2PQ to also give you a ratio. So I'll leave that. That way you guys are still able to work with calculating ratios under Hardy-Weinberg equilibrium without really giving you the answer too much. But
Okay.
this should have been provided. On an exam, I don't anticipate questions will be like this.
I
Okay.
will tell
I
you
feel
guys
like
from my experience, some of the recitation questions are usually at a higher difficulty level than you'll get on the exam. So the highest level difficulty problems on your recitations are not going to be represented on the exam. They won't be that difficult. They'll be more like the moderately. Does that make sense?
it makes sense, but like, I don't know. I mean, I know it's not your guys' fault, but it's like I feel like a lot of the problems are like this, and then I get to the exam and then I'm just lost just because I can't even figure out these problems, if that makes sense.
Mm-hmm.
Right. Yeah, I mean, um, like my way of learning is kind of through like momentum building. So I totally feel that where recitations like this and your activities should kind of build your momentum into the exam and give you the tools that you will need. So are you saying more that maybe the questions don't translate as well to the exam?
Yes.
Gotcha. Yeah, and that's something that's tough too because um especially for first time TAs, or really even if I were to TA this like a second and third time, the TAs don't have access to exams until, they're released. So unless we document questions from previous exams, maybe we can format recitations that we build um, to make them more translatable. But the only advice that I would have is to make sure you go over the exam review. I don't know if that was helpful. I wasn't able to watch the recordings from that, but yeah, I don't know. I'm
It
sorry
was
about that.
helpful. I just think it was like so much material where it's like we were more trying to like get through it than like just me. I'm just a slow learner. That's just, like I've always been like that.
Mhm.
So I just like it was just hard for me to, even though I know I have to do my own work on the side and I'll probably go over it again. It was just like so much material where it's like I don't know, maybe if there's like a better way to put it and like condense it maybe and go slower throughout the material. It was just so much that like we were just kind of like trying to get through it because we were going like past the 2 hours. It was like we almost had like 3 hours or something like that. So it was a lot.
Oh, for sure.
Yeah,
Yeah.
it's super fast and condensed. I give you guys a lot of credit for bravery for taking on genetics in the summer.
Yeah, I don't know what I was thinking. I don't know why I thought. I don't know. I think I just had too much confidence because I was like, "Oh yeah, I'm gonna do this," and now I'm like, "Oh no."
Right. Right, because yeah, so I just finished up the first year of my grad program, so I've only been able to like TA once before, and it was for Bio 340, and it was an in-person one. And over the semester, like I thought that was fast. That was over an entire 16 weeks. And when I heard that you guys were going to learn it in 6 weeks, I was like, wow, that's impressive. Like even if you get through this course in general, like, that's I would say that's a big achievement in general.
Yeah. I was actually asking the girls yesterday, and I don't know if you know anything, but I do want to do like more practice problems and maybe more that are not as complex. Do you have any like suggestions on what you would do?
I would probably, I don't know if um you like to watch videos. Christopher probably has a good idea of what to do also because I assume you took this class online also.
I did. Yeah, I took
Okay.
it in the spring. So,
Oh no, Amanda. Yeah. Um, I don't know. I'm a big video watcher because I'm also pretty visual and I like animations that they do for genetics material. But Christopher, if you have like any websites that actually have like activities that you can do, free ones, because I feel like a lot of
uh, off the top of my head, I can't think. I mean, you can always just go to YouTube and type in Hardy Weinberg equilibrium. You could listen to other people's lectures, and they'll probably go over some sample problems on there as well. You could even refine your search to Hardy Weinberg equilibrium, basic problems, moderate problems, advanced problems. You could scale it like that.
yeah, so sorry, we don't really have like a specific thing.
No, it's okay. I'm just probably gonna go through like all the videos from last week and this week again and probably just try my best.
Yeah, that's what I did.
Yeah, that sounds good. So you guys have three more exams, and that includes the final. I mean, with the lowest score being dropped, hopefully that helps. Um, but I'll see what I'll reach out to Dr. Holacek too and see if she has any ideas, just so I know in the future also
Right. So,
what.
Luke, this Dropbox is not giving me anything right now for some reason.
Mhm.
Let me see. I'm wondering if there's a way for you to just DM me on the Discord what he has as the answer, so I have that. If
Definitely.
you get a chance to do that, go ahead and do that on the burn book, or you could just DM me, and then I'll have those. I'm
Sorry,
gonna
what do
have
you,
to check out. If I were
okay.
you guys, I would table these until you get back with Wang Shang,
Yeah. Yeah,
because I
definitely.
think you're going to be going in circles.
I agree. So definitely use the info that like knowing P and Q for this problem is going to be able to give you the ratio. Um, but and then also for question four, I think you'll be able to use that now. We also went through that, but you're right. Yeah, definitely attend his office hours on Wednesday to see how he was thinking about this problem. Um, Even though I don't anticipate there being a problem like this one on the exam, you will have more information.
What
But
I can see happening for you guys, just so that this might calm you guys down a bit about your grade for this recitation. When this happened in my course, they just basically got rid of that question for the grade. because they weren't able to get back to everyone in time for them to be able to solve the problem the right way. So what I would think is what would happen is if there is a real problem with these two, whatever you guys submit tonight, it'll be regraded later appropriately. I hope that helps calm you guys down on this one a little bit. But with that, I gotta go, guys. I gotta get back to work.
Yeah, thank you,
Thanks for
Christopher. Yeah, hey, if you do have access to the questions on Dropbox, it is on there as question 2.
Okay, I'm gonna keep trying to get that.
Okay.
If not, yeah, if you do get a chance to send it to me personally too, that would be appreciated.
That
Okay,
sounds good.
guys, I'm checking out.
All right. Thank
I
you.
will be at Wang Cheng's office hours on Wednesday too. So,
Perfect.
okay,
See ya.
see you.
Cool. Okay. Let's see what else. So what other questions do you guys have? Do you guys have any more? But yeah, once again, sorry about these questions. We have a meeting tomorrow with Dr. Holacek, all of us TAs, and I'm going to bring it up just because these questions are really tough. Were there any other ones on this quiz that you feel like were kind of similar, where they just felt like kind of impossible?
I haven't went through this is honestly my first time seeing it, so no, but I'll
Okay,
probably join office hours later or tomorrow if there's any later.
that sounds good. Um, let's see if I can like, since it's my first time using this like annotation thing. Oh, cool. Okay, that's easy. I was like trying to figure out how I was going to erase all of that. Okay, so yeah, looking at the rest of the questions, I thought that the rest of them were pretty straightforward. I imagine he goes over testing this hypothesis in his PowerPoint. And then down here, he also does have a few slides that are helpful. Knowing the alpha value, which is, going up and down, or like the columns, and then the degree of freedom, which are the rows. So you're just going to locate 0.05 and 1. That one's pretty straightforward. And this is also just part of the chi-square calculations and how that relates to whether a population follows a Hardy-Weinberg distribution or not. Just putting it into words. I think that should also come from the PowerPoint. Um, and then I'm pretty sure this, you'll be using the table that was present 2 questions ago. So it's a lot of math on this one. I don't know. I used to be good at math, but honestly, it kind of scares me now. And yeah, I would say those two, as I was looking through this, were the hardest questions. Well, hardest as in like kind of like borderline impossible, but okay.
Hi, can you hear me?
Yes, I can.
I got a question on question 11. I feel like two of the answers could be possible, but I don't know
Uh-huh.
which one would be the best one to use.
So let me look at that question. So which 2 answers were you thinking?
The first one, a dominant allele confers a markedly higher survival rate, and the second one, I believe, large numbers of immigrants bring new alleles into the population.
Gotcha. So I would say that those two like answers are pretty uh close to one another. I mean, people who study population genetics, obviously Hardy-Weinberg is never really present in actual populations because of like the vast amounts of immigration that happens all over the world and bringing new alleles. So the Hardy-Weinberg equation changes from what it was. But if those new alleles can be integrated randomly also, and there's like random selection, random mating, you can still follow Hardy-Weinberg equilibrium. You would just have more alleles to work with. That's at least how I would go about this question. So ultimately, looking at that top option that the dominant allele confers a higher survival rate, I think that might actually break the equilibrium more. Like that's like might be a better answer if that makes sense.
Perfect. Thank you.
Yeah, of course. Cool. Yeah, of course. Yeah, if you guys don't have any other questions, we can call it a day. Thank you for bringing that to my attention, like some of the questions about, uh, well, really just questions 4 and 5 that were needed a little bit of additional information. So, but yeah, if you guys don't have any other questions, I'm gonna stop the recording, but feel free to go back to it if you need to like relook at this information.